Good afternoon, good evening, people around the world who are watching us today in our ACigs webinar, 21st of October 2020. So we're going to have a very interesting presentation today from Stefan and Gus. I'll just take you through the introduction slides. As all of you know, ACigs is the Australasian chapter of IGS, and IGS is the Global Geosynthetic Society, International Geosynthetic Society, more than 45 chapters, and ACigs is one of those chapters. 4,000 individual members, 500 student members, and 190 corporate members. And ACigs covers Australia, New Zealand, and Pacific Islands. So the website for Global Society, International Global Geosynthetic Society, is www.geosyntheticsociety.org. When you become a member through the chapter, then you get access to all of the technical resources, as I've shown on that slide. And you can get papers from 2 prestigious journals in geosynthetics for free. Using your membership login details. Also, ACigs website, which is www.acigs.org. And also we have lots of resources on our website, including the recordings of all of the webinars we've had since August 2019. And also you will see details about the events that we're running in the future. And also you will get information about different membership levels that you can join using those ACigs membership levels. Here's a screenshot of some of our recordings of the previous webinars and lectures. So that's available to you through the website. Also, when we finish the webinar, you can request a certificate of attendance, and we're happy to provide that to you. We won't send it to everyone, but we can send it upon request. So you need to email us. Just make sure you send an email to info@acigs.org, and we can provide that certificate. Today's webinar, first of all, I want to thank our sponsors for this event. WhoScare is the sponsor of this event today. We thank WhoScare for the support. And the topic of the webinar is active geocomposite barriers for subaqueous capping. And it's being presented by Dr. Stefan Niewarth. A little brief biography from Stefan. So if I can minimize that. Okay, Stefan has a master and doctoral degree in civil engineering. He has worked on research projects in geotechnics and construction management. In his dissertation, he developed an awarding model for public construction projects with which operational and environmental award criteria can, beside the price, be taken into account in a legally watertight manner. He then worked for a contractor and was involved in different construction projects at Geosynthetics. He has been working in business development for environmental engineering since January 2020. He takes care of technical support in capping projects worldwide and the further development of active geocomposites. Before we go hand over to Stefan, I just thought I'd share this little paragraph from Sir David Attenborough. He's recently joined Instagram, and I really like his posts and little videos on Instagram. So this is part of one of his little videos. David says, "I'm often asked, what is the one thing that would really make a difference? I don't think there is one single thing. We all live such different lives. But there might be one approach that could make a very big difference indeed. I call it rewilding the world. But in practical terms, it means putting nature at the heart of our decisions. If we can move from viewing nature from something nice to have to seeing it as the most fundamental factor in our civilization, we would make decisions very differently." So that was a quote from David Attenborough. And thank you. I just stop sharing from my end and hand over. The floor is yours, Stefan. And I also have Gus Martins on the panel today, so he will provide us with some case study after Stefan's presentation. Stefan, over to you.
Yeah, thank you very much for the introduction, and hello to everybody who's listening. Good morning, good evening, good afternoon. My name is Stefan Niewarth, and I'm the Business Development Manager for Environmental Engineering here at HÜSCA in Germany. And I'm very happy to show you some impressions today about active geocomposite barriers for subaqueous capping applications. And I will split this presentation together with my colleague Gus, who also is in the business development for environmental engineering, located in Australia. Okay, yeah, let me start. I would like to start with the problem and different remedial options, and then I will go on and show you something about the designing of an active cap, and of course the hero of our active cap, which is the active layer. And then I will show some pictures about underwater installation before I will hand over to Gus, who will then show you a study case which we've done, I think, almost some weeks ago in Sydney. So what's the problem? The problem is that different contaminations enter our environment on a variety of ways. Mostly we don't hear from it. We only hear from it when there are big catastrophes, like I think you all have heard from the oil disaster very close to the coastline of Mauritius in this summer. Yeah, when there are these punctual events, we hear from it in the news, but mostly, and this is the topic today, we don't hear really pretty much about it, how contaminants enter our water bodies. And what you can see on these two slides is a river. It is the Portland Harbor in the USA, where there's much of industry very close to the river. Yeah, we have different industrial plants, different power plants. We have the ship loadings and unloading ship traffic here. And due to all these processes, lots of contaminants enter our water bodies. We have a variety here on different contaminants that we have to deal with. And yeah, as environmental problems get more and more seen by the by us as humans, yeah, these problems get more in focus. When it comes to the question how to remediate a site, it's always in the beginning very important to do site characterization. And of course, we have to know in the beginning what types of contaminants are there. There are all these, when you listen to, when you read the reports, the lab reports, then you can see all these abbreviations like the TBT, PCB, NAPL, PAHs, VOC. And then the question is, what is it? What are the mechanisms? Are they harmful? Since what amount are they harmful? And of course, it's also the question, where do they originate from? And yeah, there are different, or they origin from different industrial processes. As you can see here, this is another picture from the Portland Harbor, where you can see what type of industry is very close to the river here. And I don't want to go too much into detail, and I can't go much into detail about all these different contaminations today, but I want to give you a short picture how or where the different types of contaminants originate from, yeah, so that when you know, okay, my construction site is very close, or my remedial site is very close to, let's say, a former gas station, then you know, okay, I will probably have problems with this or that contamination. This, of course, ends where you have all the different industries very close to each other, as you can see here in Portland Harbor, where we have the oil industry, the gas industry, woods, we have paper mills, we have almost everything really close on or along the river. So they will have everything of these compounds inside the river. Especially today, we want to talk about the organic compounds, where we want to focus on. So this is a slide where I try to put in the different industries into the groups, or I want to show here what kind, when you know, for example, as I said before, that you have to deal with a remedial site that is very close to, let's say, a pipe paper mill, then you can imagine that probably you will have tributyltin in the sediments. This results because of the industrial process in the first step, and of course about the materials and the products that a paper mill use. Another example is when you have to remediate sediments very close to a landfill, for example, or to a gas station, you will probably have volatile organic compounds in the sediments. This is not the only contaminant that you might have, but it could be the one that is in focus. Yeah, so you can have a look afterwards on this slide, because I think the webinar is recorded, or just send me an email and I can forward this slide to you, because I think that it very nicely shows what industries leads to which contamination or which problems. When we have done a site characterization and we know what contaminants are there on site, we can think about what could be the best remedial option. And there are different options. Mostly, there are three bigger groups that we talk about. The first thing is the monitored natural recovery, which means that we measure the concentration of the contaminants in the water body, in the sediments, also in the biological organisms like in algae or in fishes, and then we see how the contamination develop over the time. And when we see, okay, there is a decrease of the concentration up to a minimum, then we don't have to do remedial actions. We only have to measure it and see that it will not increase again. The next thing is the dredge and dewatering, where we use, I don't know if you can see my cursor, but here, like in the upper picture, you can see a dredger, which we can use to remove the contaminated sediments and pump it away from the site, and then they are not longer in the river bodies. Afterwards, they have to be dewatered with the help of centrifuge or filter presses, or also dewatering tubes, of course, before they can be then disposed on a landfill. This techniques leads to high energy consumption because of the big machinery that is used. But in the end, you can be sure that all the contamination or all the sediments, when you do it properly, are not in the river body any longer. This is not the case when we do an in situ capping, which is our topic today, but of course it also has other advantages. In situ capping can be split into three undergroups. The first thing is a conventional cap, where we just bank up a very thick sand layer on top of the contamination in order to get a chemical isolation of the contamination. And the next thing is an amended cap, which you can see here on this picture. Here you can see that in an amended cap, different active materials can be mixed in the sediments in order to get a chemical isolation. This black active material here is an activated carbon that is mixed in the sediments to have this isolation layer. And the third thing, and this is on focus today, is the active capping, or the capping with active geocomposites, which means that we have a geocomposite, so two layers of non-woven material and in between we have a constant thin layer of the active material that that is rolled over the contaminated sediments, and then we have to place a thin sand layer on top of it. And yeah, then we also have built a very proper cap to isolate the chemical isolate the contamination. This slide here is from Dr. Danny Ribel from the USA, and it compares the different remedial options with regard to the relative risk that result from it. And what you can see here is the level of the relative risk over the time, and we can see different remedial options. The light blue one here is the natural recovery, and we can see that in the beginning the risk is 100% because we haven't done anything. We just start with our measuring and controlling process, and over the years then the relative risk decrease because the flux and the concentration of the contaminants also decrease. But however, this takes some time. Yeah, it takes 50 years in this simulation until we have a risk of, I don't know, 30% or so. The other option would be the dredging, which is the orange line here. When we do a dredging after 6 or 7 years, in the beginning, we will have a strong decrease, because you can imagine that when you dig in the contaminated sediments, then all these contamination and all these sediments spread it in the water body, and it's inside the water body before we dig it out. And when you have digged out the first meter of the contamination, then the next meter is in the surface, and it can it might be that after the first meter, the second meter even has a higher concentration of the contaminants than the first meter. Because of all these facts, with the dredging option, for the first time you might have or you will have a higher risk because of all these sediment spreading. But then afterwards it fastly go down and then come down to a very slow value. When you do the capping, you will have an immediate risk reduction from the point when you put the cap on top of the sediments, because you don't have any spreading of the sediments. You just place a layer and you will have a chemical isolation, which reduces our risk to a very low level. You might have breaches over the years, but then also the relative risk slightly rises and then goes back to a low value. Yeah, why capping? Why do we do a capping? The first and the most important thing is to prevent the bioaccumulation along the food chain. This is what you can see here on the picture. You can imagine that when algae grow there in the contaminated sediments, then in the cell structure of the algae, the contamination agglomerates, and when then one shrimp eat, let's say, 5 algae, then the contamination gets compacted, so that there is a higher concentration of the contamination in one shrimp, and then one shrimp is eaten by one little fish is eaten by the bigger fish, and in the end we as human beings eat the bigger fish. And over this whole food chain, the contamination gets compacted or accumulated, and this of course in the end leads to the point that we can that it leads to problems, health problems for us as human beings. Some of the contaminants are very in the worst case they are cancerogenic, so that we as human beings have to protect ourselves against these contaminations. Why do we do it? Why do we do capping? We want to evaluate a long-term risk reduction under appropriate condition, which means that the function, the isolation of the chemicals, this function is fulfilled over the whole lifetime, of course. We have to minimize the impact on the function of the waterways. So we don't want to reduce the water depths so much that there's no ship traffic possible any longer. And we need these water depths also for other functions of the waterway, like flood storage and so on. We don't want, or we want to have a short construction phase, of course, with the immediate risk reduction, as I said before. And in the best case, we don't want to have high costs and high risks for example, for the removal, the treatment, and the disposal of the soils. These are all advantages, or better say, requirements that we have on a cap design. So let's start with a conventional cap to have a better understanding to what do we have to look for. When we place a conventional cap over a contaminated sediment, we have to place, depending on the maximum contamination, of course, we have to place a thick sand layer, which can be 1 to a maximum of 2 meters. And here the objective is to ensure the function of the chemical isolation, as I said before. Why do we need such a very thick sand cap? We have different layers. Yeah, please imagine all of them are sand, but they fulfill different tasks. We have different influences, and for all these influences, we need a certain thickness of this sand cap. For example, we are in a very high energy environment where we have erosion and advections from currents, from waves, from ship maneuvering. We have subaqueous groundwater discharge from the ground to the rivers. We have bioturbation, which means that little organisms like worms or shells dig inside our sand cap. There are things like slope stability and bearing capacity, of course. We have placement uncertainties. You can imagine that when you put water from above the surface of the water in the water body, then all the bulk material slowly settles down the water column, and then it ends up somewhere, and hopefully it ends up there where you want to have it, but you will still have some placement uncertainties due to this process of settling down of the sediments. Then we have issues with the mixing, of course, here with the contaminated sediment and the clean sediment. Yeah, and we have some other influences like gas formation, diffusion and consolidation and so on. And for all these influences, to make sure that our sand cap really survive these influences, we need a certain thickness for the different layer functions. Yeah, we need a certain thickness for the bioturbation layer, for the advection, for placement uncertainties and the mixing. And then in the end, for the chemical isolation, we only have something like a rest thickness that has to be ensured. So in the end, when we design an active cap, or also any cap, the design objective is to design a safe cap with the lowest possible thickness under consideration of all influences. And how can we be sure to get this? We have to reduce the effects of all external influences. We have to minimize the mixing of the layers. And of course, we have to ensure a long-term risk reduction for the maximum concentration. So how can we now reduce the thickness now? As I said before, when you bank up a thick sand cap, you have high factors of safety, and due to all the mixing and placement uncertainties and so, and therefore there's a large thickness that reduces the hydraulic capacity, flood storage, navigable depths, and so on. So therefore, we don't use a thick sand cap, but we can use active material. This active material has ensures a better chemical isolation for different contamination. So when you know which kind of contamination you have on your remedial site, you can choose the best active material to fulfill this function of chemical isolation. But there are also difficulties with it. It's the same as I said before with the installation of bulk material that settles down. It's a problem, especially on slopes and when you have currents in the water. And also here, mixing remains an issue. Therefore, we can use geotextiles in an active geocomposite. This prevents the mixing of the contaminated sediments with the clean sediments in the cap, and it really ensures on a plant, so we can be sure that on every square meter we have the same unit mass, and therefore we can, when we roll a geocomposite in the water, we can be sure that we have the same layer thickness across the whole covered area. But of course, there are other things that we have to take into account, like the sinking process of these very light material that might need additional support. And here, this is something like a summary of that what I said before. When we use an active geocomposite, we don't need the advection layer, we don't have placement uncertainties, and we don't have mixing. Therefore, the chemical isolation layer is much thinner than with a sand cap, but we also have to place a very thin sand cap on top of the active geocomposite in order to prevent the textiles against damages, to prevent it against UV radiation, and also because we want to renaturate our river bodies, and we want to make sure that in the seabed new algae can grow, and therefore we need a sand cap. When we then come to the design of the active geocomposite, the next thing, or the first thing, is to choose the best active material and the best geotextiles that fulfill the requirements that we have on site. So I now want to go a little bit more into detail about the active material. Depending on the type and quantity of the contaminants, we can choose different active materials this is the target, of course, to significantly reduce the contamination transport. And there are different active materials that have been proven by practice and that have been demonstrated very well. This is especially clays, activated carbon and biochar, and the organophilic clay. And at Husker, we also use the AC, the activated carbon, and the OC, the organophilic clay, in order to deal with organic compounds. And we also deal with other things like, let's say, something like an apatite to create a barrier against heavy metals. But today we want to focus on the organic compounds, and therefore these three active materials I want to go focus on, and these are the ones that also are proven by practice and demonstrated very well. Okay, the activated carbon, why does it work so good? It is a strong organic absorbent, so the material itself is organic, and therefore it works very well with organic substances like the tributyltin, polyaromatic hydrocarbons, VOCs, PCBs, etc. And it works so well because of the high surface area of the material, because of the micropore structure. Inside an activated carbon, you will find different pores. You will have macropores, which are the largest one, mesopores, which are the intermediate one, and then micropores, which are the smallest one. And you need all these different pore sizes when you have different sizes of the molecules as well. So the large organic molecules will agglomerate in the micropores, and the smaller ones will agglomerate more in the micropores. And therefore, it is very, very, very important to know what kind of molecule but to choose really the best activated carbon, we have to go more into detail and we have to see what kind of PAHs, for example, yeah, this is an advanced level in PAHs, what kinds of them do we really have on site? Because we know over hundreds of PAHs and 16 of them are representative for a group. And for example, the naphthalene is the smallest one. You can see this because it consists of 2 benzene rings and it has a low molar mass compared, for example, with the Fantabs, which has a higher molar mass and it consists of 5 benzene rings. So when you know, okay, I have this small contamination in my sediments, then it's better to use also an activated carbon with a fine porous structure. And this can be an activated carbon made from coconut shells. And when you, on the other side, know that you have more of the large molecules, then it might be better to use an activated carbon made from hard coal or made from wood. Yeah, and therefore an activated carbon is not an activated carbon, and we really have to know what kind of contamination do we have on site. And then all these activated carbon, these ACs, have its different advantages and disadvantages. One thing is the price. Yeah, the coconut shell is the most expensive one, and the wood is it's a bit cheaper. And this is also when it comes to price questions, and customer ask us what will be the price of an active geocomposite, and we have to say, okay, we really have to go into detail here to get a serious pricing, because we have to see if we need coconut shell or if we need wood. And yeah, there are also other advantages and disadvantages, like the coconut shell has a higher activity due to high porosity, low initial level of pollutant, and the advantage here is then the disadvantage here, and so on. So they, yeah. Time, but I want to focus here only on 2 graphs in the diagram. So what can we see? We can see it's also a simulation made by or done by Dr. Reibel, and he measured the flux of a PCB on the surface of the sediment. So he measured it at the interface between the water and the sediment seabed. And I only want to have a look on this blue line here, which shows us the existing conditions that we can measure without doing anything. So like the MNR remediation technique, and where we see that over the time the flux decreases at the beginning from a high value, and then after, let's say, 30 years, it comes to a steady level here, but then the decreasing ends, and the flux will be on a certain level for the whole time. And then the level down below here is a 30 centimeter AC amended sand cap with a 1 centimeter AC met. So 2 types. One thing is the mixing of bulk AC with the sediment, and then on top of it we place a 1 centimeter AC met, and then we will measure nothing more. And of course there are other techniques or other capping designs here somewhere in between, like the sand cap here, yeah, it's somewhere in between, and also other ones. What I want to say here also, sorry for that, yeah, that simulation can really be done very well. For example, with the tool from Dr. Reibel, which is a capsule model, you can really simulate how the flux will develop over the time. Okay, then the next compound in our active geocomposite is, of course, the geotextile. And typically there are 2 layers of non-woven, which are stitch bonded or needle punched together. So stitch bonding means to really soon these two, the upper layer and the lower layer together, and then this leads to these wave. It looks like these waves here. And at Husker, we also use, for our active geocomposite with activated carbon, we most often use the stitch bonded technique, because the unit mass that we can bring here in the active geocomposite is higher than with the needle punching technique. Also, there's the question that we always get is, oh, do I really have the certain thickness here in between the area where it is tuned? And yes, of course, we can also ensure that there's the unit mass that we have on the full area is also here in the soon area, so we don't create any something like breaches or so. Then the GeoTextiles has a high tensile strength. We can also increase it when we use other materials, but it is normally 15 kilonewton per meter in the machine direction, so in this direction here, and also in cross machine direction here. And the durability of the GeoTextiles is more than 100 years under normal conditions, which we have in almost most of the rivers, but project requirements might reduce the design life a little bit, but you can say that normally the 100 years is a good time for the design life, because the GeoTextiles are, when you place a sand cap on top of it, when you properly install it, then it is prevented against damages, and the durability or the design life of 100 years is a good value. So with regard to capping application, there are some advantages for the GeoTextiles. So the GeoTextile increased slope stability and bearing capacity. We haven't talked about that in this webinar, but this is for you to know it. It has a high chemical resistance. There are different materials also with the GeoTextiles that can be selected, and we can, when they are really, when we are in a very chemically environment, high or different chemical environment, and we can also choose materials that fulfill all the function and that have the resistance that we need. And we have, as I said before, a long design life of approximately 100 years. But of course, there are also failure mechanisms with the GeoTextiles in capping applications, and I also want to show them here. You can have issues or mechanisms like the washing away of a filled material in case of breaches. You can have a perforation of the GeoTextile by puncture. So this is very, it comes from the installation process. When it is not done properly, you might have puncturing. You can have issues with the rupture of seams and joints. You might have occurrence of S-shaped profile under the filter layer and a slope, and you can have damages during the installation process. And therefore, of course, choosing the right GeoTextile is very important, but also it is very important to choose the right or the correct installation equipment here. Yeah, you can see this picture here shows different GeoTextiles, and you can, I think that you can just imagine that some of them has a higher tensile strength as other ones. So this is the first thing to prevent damages, but the next thing is that we really use the best installation methods. And I quickly want to show some pictures here till I hand over to Gus. What you can see here is an installation with a long reach excavator where the active geocomposite is ballasted by these guys here and then rolled out, and afterwards stones are dropped to ballast it, to ballast the mat. Another installation technique is with the use of a barge, where you unroll the geocomposite from the barge and moves the barge away from the shoreline to the water body, and then place sand on top of it. And also you can stitch together some rolls, so to have a bigger panel like that what you can see here in the left picture. There are, I think, 3 or 4 rolls stitched together, and then they can be unrolled in only one construction process from a barge, so that you can really in a short time cover a wide area. And this is it from my side, and now I want to hand over to Gus. I think I have to stop my presentation. And Gus.
Well, thank you, Stefan. Well, first of all, we're going to show a few examples of installation here and present a study case here in Australia, in Sydney. But before starting to show the study case, I just want to present Hisca for those who don't know us yet. Hisca started more than 150 years ago as a cotton lining producer, and obviously evolved a lot to become one of the most recognized companies for geosynthetics around the world, where the majority of our products is produced here in Germany in 3 manufacturers, but we also have 3 other plants around the world, in Brazil, United States, and Russia. The majority of the products is produced in Germany, but we also have some particular products that we can produce for remediation and other environmental projects, just like we were discussing today. We usually custom made the solution to attain the exactly necessity or the exactly parameters that we have on each and every project. Usually every year we produce more than 40 million square meters of geosynthetics, and 1 in every 7 pretty much the only company that can do in the whole world is to create a geosynthetic grid that materials are for roads and pavements, for asphalt and pavements reinforcement, for earthworks and foundations, when we work together for geosynthetic reinforced soils and other low bearing capacity reinforcements, for the environmental engineering, not only for the remediation works, but also for lining on landfills, contaminated soils with other kind of materials, cappings, tailing pounds, slurry desiccation, water containment. There are several other applications that we could support the projects. For hydraulic engineering, we work mostly with erosion control and canal revetments to reduce water seepage. And we have obviously the mining area, where we provide several geosynthetics for diverse applications, including the longwall recoveries. So to come into this study case here in Australia, I would like to talk a little bit more about what used to happen in this site. It was a former AGL facility, a gas work company. This picture is pretty much in the 1950s, 1960s. And we can see here where the barges would arrive and receive coal, and obviously not just the barges and the movement of material to the facility, but also there are contaminants that were released in the water by the same company, because of the production of the and treatment of the coal. So obviously this caused a lot of impact for the environment, including the contaminants with PHLs and heavy end PTHs. This was found in 2004 and declared by the EPA that requested the remediation works to start. Obviously, this is a lot of work, include a lot of work, so they need to create a plan on how to treat the area. We can see on the left-hand side that the red area where we used to have the former facility, it's now a high-end residential area. So any kind of movement of material, if we decide to dredge the material and remove the material, will be really complex and bring another challenge to the project. So they decide to use and make any kind of movement to the project using the barges through the water. So in 2018, we start developing a solution with the main designer and the main contractor, trying to find a solution to cap the material using a geocomposite. So we came across a few solutions, and the one that was used for this particular project, this is the production of the exact material that was installed here in Australia. It was 2 non-wovens with activated carbon layer with 3,400 grams per square meter, which will be enough to contain all the contaminated soil and cap the area. And later on in 2020, we start the works on site. Firstly, obviously, trying to isolate the areas with sheet piling and sealed lines, bubble curtains. And then after this, they started installation of the geocomposite. This material is really peculiar because the same reason that makes it so unique, the activated carbon, it has a lot of area to absorb all the contaminants. It also traps a lot of air when you are placing on the top of a surface, on the top of the water. It will sink, it will not sink, it will float because of the air that is trapped inside of the particles. So this is the reason why we had to use a sinking frame. This is just one of the solutions for installation, but we had to use a sinking frame to place the material on the bottom of the water, and then place the covering material was a thick layer of sand and then rocks on top to avoid any kind of damage to the geocomposite that will be actively capping this contaminated soil. So for the installation, they used 3 barges, one smaller with the Tactor Seal active with activated carbon, one for the frame to be moved around the area, and one to transport all the ballast and top covering material. On this image, you can see that pretty much we already had 3 panels that were installed, and we were reaching the 3rd panel there, covering all the area with the sand and a layer of rocks. And we can see the overlap on the left-hand side. It was pretty much something around 500 to 1 meter, depending on the condition on site. So before opening the session to questions, I just want to show a quick video of the installation process. And obviously, if you have any other doubts, just send us an email. We're more than happy to support you and try to find what is the best installation, and obviously what is the correct material for your application. So this is the process where we move the frame, stretch the material obviously firstly, and then we move the frame on top of the mattress to bring it down slowly to avoid any kind of damage to the geocomposite. And then we can start placing the covering and the sand and rock layer on top to protect the material from UV and other kind of damage. Well, thank you all for joining us. If you guys have any questions, just please use the chat feature to send us. If it is something a little bit more complex, we are happy to support you directly. And if you have any kind of project that you think it might be suitable to use this kind of project, just obviously just get in touch with us. So Nyaka, back to you.
Thank you. Thanks, Stefan, and thanks, Gus. So we just start with a couple of questions. One question was, interestingly, the one that we were chatting about before we started the live session. Stefan, can you guess what the question is?
No.
PFAS.
PFAS. Ah, yeah, of course. Yeah.
So yeah,
yeah.
can you just tell us about, maybe just a brief about, what you've been working on recently and with this particular product as well, to contain PFAS contaminated material?
Yeah. Yeah, at Huska, we are working on a solution for PFAS contaminated soils. So we are looking for to create a horizontal barrier with our mat solutions. And all the water. So imagine that when you place a mat, and then on top of the mat you bring up the contaminated soils, and due to the rain and water processes, the PFAS are washed out from the contaminated soils, and then they will run through our mats. And then the idea is not to have something like so that the mat is permeable, so that the water can run through, and then the active material inside it will absorb the PFAS. We are very I think that we can have a product hopefully in the beginning of the next year.
Okay. Can you still hear me?
Yeah.
Yeah.
Yes.
Okay. So I think my connection was a bit weak. So another question is about durability of the material, especially when you use them for a capping application. What sort of comment do you have on the durability? How do you test the product for durability? And is there a way that that you can test it after the construction, or maybe during the operation as well?
It's a bit hard to test it after the installation process, but the material will be tested before. They will be tested, on different stages. So first time it will be tested when the non-wovens get produced, and then the raw material get tested, and then after we stitch bond it together, so after the production of the active geocomposite, so when there are two non-woven stitch bonded together with the active material in between, then it will be tested one more time. And there are different things, different lab tests that you can do there. You can simulate different properties, and we do some of these tests in our own labs here in Germany, so that we can really be sure that the durability of 100 years, or as I said before, might be a bit lower when you have different different or challenging environments on site. But of course the material get tested and certified for something like a durability of 100 years.
Okay, very good. The other question is about installation quality assurance, specifically with like subaqueous applications. How do you test the quality during the installation or once it's installed underwater? How do you make sure that the panels are all in place? There's no sort of gaps between the panels. and the quality of installation is achieved.
So, on this case, in Sydney, we had the company was using divers, obviously to guide through all the process. So the lines, they created lines marking all the overlaps and how the process was done. As soon as they finish all the layout, they would dive again and check the installation for any kind of damage of the material and see if they need to adjust or redo some part of the works. So constantly on subaqueous capping, we need to use divers as well to check all the installation process along the way.
Okay, now that's very interesting. And I just have time for maybe another question. This is, again, somehow related to the durability question, but I think, the active material, must have a limited life or like a certain amount of lifetime. So the question is about, when the material or when the active material are exhausted. Like, first of all, how do we know about it? And secondly, how can we remediate or cap or maybe do some more work to increase the life of the material?
Yeah, so of course you can measure the flux contamination above the cap, and when you then measure that you have a higher flux, then you know that the active material don't work any longer, and then you might have to see what or you have to think about what you can do then, and then something like, of course, you can amend something like a new cap on top of it, and there on this area where you really measure a higher concentration. So you don't have to cap the whole area when you see that there are spots where the contamination flux is higher, then you cap this area one more time. But the time being, I don't have heard from something like that before. Yeah, because the material works really well, and we start creating capping project since, I don't know, not since 30 years, but for a shorter time, and I haven't heard from any damages or breaches or construction sites where we really have problems with the active geocomposite.
We can't hear you.
I can't hear you. Yeah.
Yeah, I reckon we lost Simiak audio there. If we have any other questions, we are always happy to reply. If you guys have any other questions, just please send us over or to ACigs, and we'll be happy to reply. I reckon we don't have any more audio there. Yeah, I think we lost you.
There's one more question I've read. course, yeah, you can. We said that it's no problem to install it when you have a velocity of, I guess it is 1 meter per second. Then when the velocity is much higher, of course, it's getting difficult, but 1 meter per second, I guess it was, and then installation is no problem. Yeah, I think we have lost Simjak.
Yeah, well, Simjak, can we finish?
Yeah.
Well, so yeah, well, we'll close the session. If we have any other doubts, please just send us through. We are happy to support. We're going to finish the session now. Thank you all for attending, and have a good afternoon.